Hello and welcome to the Quiet Cosmos. If you enjoy calm journeys through space and gentle explorations of the universe, consider liking the video and subscribing to the channel. And as you settle in, I'd love to know, where in the world are you watching or listening from tonight? Perhaps beneath a clear sky filled with stars, or maybe somewhere the clouds softly hide them from view. Wherever you are, the night sky above you is never truly still. Even on the quietest evenings, when everything feels calm and unmoving, the stars shimmer softly, flickering, dancing, almost as if they're alive. It's something many of us notice without thinking too deeply about it. A gentle sparkle, a quiet rhythm, a kind of cosmic breathing. But that subtle twinkling isn't coming from the stars themselves. In fact, those distant suns, many of them far larger and more powerful than our own, shine with remarkable steadiness. Their light travels across unimaginable distances, through the vast stillness of space, unchanged for years, decades, even centuries, until, in the final moments of its journey, something begins to shift. The air above us, thin, invisible, and constantly moving, quietly reshapes that ancient light. What appears to us as a flicker is actually a story of motion in the atmosphere, of light bending and shifting, of tiny variations that ripple across the sky faster than we can consciously follow. It's a reminder that even in stillness there is movement, even in clarity there is distortion, and perhaps most interesting of all, the twinkling we see tells us just as much about Earth as it does about the stars. Tonight, we'll take a slow and gentle journey through that story, from the steady hearts of distant stars to the restless layers of our atmosphere, to the quiet way our own eyes and minds bring it all together. And by the end, the next time you look up at a twinkling sky, you may find it feels just a little different, a little deeper, a little closer, and perhaps a little more alive. If you've ever stepped outside on a quiet night and looked up, you may have noticed how the stars seem to shimmer softly, as though they are gently flickering in place. It is not a dramatic movement, not something loud or demanding attention, but something subtle. A quiet sparkle that feels almost alive. There is something deeply calming about it, even in the stillness of the night, when the air feels calm against your skin and the world seems to pause. The sky above you is quietly in motion. Points of light that have travelled for years, sometimes for thousands of years, arrive at your eyes and appear to waver, to brighten and dim, to shift ever so slightly. It can feel as though the stars themselves are changing, but they are not. What you're seeing is not a change in the stars, but a change in the path their light takes just before it reaches you. And in that sense, the twinkling of stars becomes something more than just a visual detail. It becomes a kind of meeting point, a place where distant reality and local conditions overlap. The philosopher of science, Bas van Fraassen, once explored the idea that what we observe is not always a direct window into reality itself, but rather an interaction between reality and the instruments, environments, and conditions through which we observe it. In his work on constructive empiricism, he suggested that science is concerned with what can be observed, but that observation itself is shaped by context. And here, standing beneath the night sky, you're experiencing that idea directly. The stars are steady, their light is consistent, governed by processes that are stable over immense periods of time. Deep within them, nuclear fusion converts hydrogen into helium, releasing energy in a controlled and balanced way. This balance is maintained through what physicists call hydrostatic equilibrium, where the inward pull of gravity is precisely countered by the outward pressure of energy from fusion. In simple terms, stars are remarkably stable light sources, yet what reaches your eyes feels anything but stable. Between you and those distant stars lies the atmosphere of Earth, a layer of gas extending upward for tens of kilometers, composed primarily of nitrogen and oxygen, but constantly in motion. Warm air rises, cool air sinks, winds shift, temperatures vary, and all of this creates a dynamic, ever-changing environment. So the light that left a star long ago, travelling in a straight and steady path across the vast emptiness of space, suddenly encounters a medium that is anything but uniform. And that is where the transformation begins. What makes this especially interesting is that the experience of twinkling is not just about physics. It is also about perception, about how your eyes and your mind interpret what is happening. The philosopher Maurice Merleau-Ponty writing about perception, described how our experience of the world is always shaped by the interaction between the external world and our embodied presence within it. We do not passively receive reality. We participate in it, in a sense, through the act of perception. When you look at a star, your brain is not simply recording light. It is continuously interpreting small variations in brightness and position, assembling them into a coherent experience. The slight flickers, the tiny shifts in intensity, are translated into what we recognize as twinkling. It feels natural, familiar, almost expected. But it is in fact a complex interaction between distant astrophysical processes, atmospheric physics, and human perception. And there is something quietly beautiful in that, because it means that the night sky you see is not just a distant scene. It is something shaped, in part, by the very air around you. The same air you breathe, the same air that moves gently across the surface of the Earth, is also shaping the light of stars as it arrives. In a way, every twinkling star carries a subtle imprint of Earth itself. If you were to travel beyond the atmosphere, far above the moving layers of air, you would notice something immediately different. The stars would no longer twinkle. They would appear steady, fixed, almost perfectly constant in their brightness. Astronauts aboard spacecraft often describe this. The sky in space is sharp, stable, and still. The familiar flicker is gone, which tells us something important. Twinkling is not a property of the stars. It is a property of the space between the stars and us, or more precisely the space just above us, and that shifts the question. Instead of asking why stars twinkle, we begin to ask what is happening in that final stretch of their journey. What is it about Earth's atmosphere that causes such delicate, constant variations? How can something as invisible as air reshape light in such noticeable ways? And why does it affect stars so strongly, while other objects in the sky, like planets, often appear much steadier? These are questions that lead us gently from observation into understanding. Because once we begin to follow the path of starlight, from its origin in distant stars to its final moments passing through our atmosphere, we start to uncover a layered story. A story involving the behavior of light, the structure of the atmosphere, and the subtle interplay between order and chaos. It is not a sudden shift into complexity, but a gradual unfolding. And like the twinkling itself, it is something best approached slowly. So as you picture that quiet night sky, with its soft, shimmering points of light, we can begin to look a little closer, not to disrupt the calm of the moment, but to understand it more deeply. Because hidden within that gentle flicker is a remarkable story of motion, physics, and perception, all working together in ways that are both precise and beautifully subtle. When we look up at the night sky, it is easy to think of stars as distant points of light, almost like tiny holes in the darkness. They appear small, delicate, and quiet. But in reality, each one of those points is something vast, powerful, and remarkably stable. A star is, at its most fundamental level, a self-gravitating sphere of plasma. Plasma is a state of matter where atoms are so energetic that their electrons are no longer bound tightly to their nuclei. Instead, the material exists as a flowing mixture of charged particles. This gives stars some of their most important properties, including their ability to conduct energy and respond to magnetic fields. At the heart of every star lies a process that defines its existence: nuclear fusion. In the simplest terms, nuclear fusion is the process by which lighter atomic nuclei combine to form heavier ones. In most stars, including our Sun, this involves hydrogen nuclei merging together to form helium. When this happens, a small amount of mass is converted into energy, according to Einstein's well-known relationship between mass and energy. Energy equals mass multiplied by the speed of light squared. Even a tiny amount of mass, when converted in this way, produces an enormous amount of energy. This is what powers a star, allowing it to shine continuously for millions or even billions of years. But what makes a star truly remarkable is not just that it produces energy, but that it does so in a way that is extraordinarily stable. To understand this stability, we need to look at a principle known as hydrostatic equilibrium. This is one of the defining concepts in stellar physics, explored in detail by scientists such as Subrahmanyan Chandrasekhar, whose work helped deepen our understanding of how stars maintain their structure over time. Hydrostatic equilibrium describes a balance between two opposing forces. On one side there is gravity. The immense mass of a star creates a powerful inward pull, constantly trying to compress the star into a smaller volume. On the other side there is pressure generated by the energy from nuclear fusion in the core. This energy heats the plasma, causing it to expand outward. When these two forces are perfectly balanced, the star remains stable. If gravity were to become stronger than the outward pressure, the star would begin to collapse. If the outward pressure were to dominate, the star would expand. But in a stable star, these forces remain in a delicate and continuous balance, allowing it to maintain a relatively constant size and brightness. This balance is not static. It is dynamic, constantly adjusting. If the core begins to compress slightly, temperatures rise, fusion rates increase, and more energy is produced, pushing outward again. If the core expands slightly, temperatures drop, fusion slows, and gravity pulls the material back inward. It is a self-regulating system. Arthur Eddington, one of the early pioneers in stellar astrophysics, described this balance in the early 20th century. His models of stellar interiors helped establish the idea that stars are not chaotic objects, but rather structured systems governed by clear physical laws. He showed that energy generated in the core must travel outward through layers of plasma, either by radiation or convection, eventually reaching the surface and being emitted as light. This means that the light we see from a star is the final result of a long journey that begins deep within its core, and that journey is surprisingly smooth. Although stars can vary over long periods of time, and some types of stars do exhibit changes in brightness, the vast majority of stars appear steady on human timescales. Their energy output remains consistent, their light stable, their presence reliable. This understanding was significantly advanced by Cecilia Payne-Gaposchkin, whose work in the early 20th century revealed that stars are composed primarily of hydrogen and helium. Before her research, it was widely assumed that stars had compositions similar to Earth. Her findings reshaped our understanding of stellar structure and confirmed that the processes governing stars are universal and predictable. So when we observe a star, we are looking at an object that is not flickering or fluctuating in any rapid or chaotic way. It is not pulsing or dimming moment to moment. It is, in fact, producing a steady stream of light, generated through processes that are well understood and remarkably consistent. To put this into perspective, the Sun, our nearest star, emits energy at a rate of roughly 400 trillion watts. And yet from one moment to the next, that output changes only very slightly. The variations are so small that they are barely noticeable without precise instruments. Most other stars behave in a similar way. So if the stars themselves are stable and their light is steady, then the question becomes even more intriguing. Why do they appear to twinkle? The answer lies not in the stars, but in what happens to their light after it leaves them. By the time starlight reaches Earth, it has travelled across vast distances, often for hundreds or thousands of years, without significant disturbance. Space, for the most part, is an excellent medium for light to travel through. It is largely empty, with very little to interfere with the path of photons. And then, in the final fraction of a second before that light reaches your eyes, it encounters something very different. The atmosphere of Earth. This thin layer of gases, extending upward for tens of kilometers, is anything but uniform. It is constantly shifting, with variations in temperature, density, and motion. And as the light passes through these layers, it begins to change direction ever so slightly. Not enough to blur the image completely, but enough to create small, rapid variations in brightness and position. So the steady light of a distant star becomes, in our view, a gentle flicker. This creates a kind of illusion, a transformation that takes place not at the source, but along the path, and it highlights something important. What we see is not always a direct reflection of what is happening at the source of light. It is shaped by the journey that light takes, and by the medium through which it travels. In the case of stars, that journey is long and stable for most of its duration, but in its final moments, it becomes complex and dynamic, and that is where the twinkling begins. To understand why stars appear to twinkle, it helps to follow the light itself, not just where it ends up, but the full journey it takes from its origin to your eyes. That journey begins deep inside a star, where energy is produced through nuclear fusion. From there, light slowly works its way outward, moving through dense layers of plasma before finally escaping into space. Once it leaves the surface of the star, something quite remarkable happens. For most of its journey, That light travels in almost perfect stillness. In the vacuum of space, there is very little to interfere with its path. Space is not completely empty, but it is close enough that, over vast distances, light can travel with extraordinary stability. The density of matter between stars is incredibly low, often just a few atoms per cubic centimetre, and in many regions even less than that. So once a photon, which is the fundamental particle of light, begins its journey through space, it continues in a straight line unless something significant alters its path. This behaviour is described through principles of radiative transfer, which study how radiation moves through different environments. In dense materials, light may scatter, absorb, and re-emit many times. But in the near vacuum between stars, these interactions are rare. The photon moves forward, carrying energy and information from its source. It does so at a constant speed, approximately 300,000 kilometers per second. At that speed, light from the Sun takes about 8 minutes to reach Earth. Light from more distant stars can take years, decades, or far longer. Some of the stars visible in the night sky are so distant that their light began its journey before modern science even existed. And yet, despite travelling for such immense spans of time, that light remains remarkably consistent. There are, of course, subtle influences along the way. Gravity, for example, can affect the path of light. According to the theory of general relativity, developed by Albert Einstein, massive objects can curve the fabric of space-time itself. Light follows these curves, resulting in what is known as gravitational lensing. Carl Schwarzschild was one of the first to find an exact solution to Einstein's equations, describing how space-time behaves around a spherical mass. His work helped clarify how light would bend near massive objects such as stars or black holes. In extreme cases, this bending can produce multiple images of the same distant object or stretch light into arcs. But for most starlight reaching Earth, these effects are either very small or occur far from our direct line of sight. So for the majority of its journey, light moves through space with a quiet kind of precision. It does not flicker, it does not waver, it does not randomly change direction. It travels steadily, carrying with it a record of the conditions at the star from which it came. This is one of the reasons astronomy is possible at all. When we observe distant stars and galaxies, we are not just seeing light, we are receiving information. The brightness, colour and spectrum of that light tell us about temperature, composition, motion and distance. Entire fields of study, such as spectroscopy, are built on the assumption that light arrives in a form that can be trusted. And for most of its journey, that assumption holds true. Space, in this sense, is a remarkably calm environment for light. It is vast, quiet, and largely uniform. There are no winds, no rapid temperature fluctuations, no constantly shifting layers of density. Compared to what comes next, it is almost perfectly still. And then, after travelling across unimaginable distances, the light reaches the final stage of its journey, Earth's atmosphere. This is where everything changes. Unlike space, the atmosphere is dense, dynamic, and constantly in motion. It is composed of layers of gases, each with slightly different temperatures and pressures. Air currents move continuously, driven by solar heating, rotation of the planet, and complex weather systems. These movements create variations in density, and density affects how light travels. When light passes from one medium into another, its speed changes. In a vacuum, light moves at its maximum speed. In air, it slows down slightly. And when the properties of that air change from one region to another, the path of light bends. This bending is known as refraction. In a perfectly uniform atmosphere, refraction would occur in a smooth and predictable way. The position of a star might shift slightly, but it would remain steady. But Earth's atmosphere is not uniform. It is filled with constantly shifting pockets of air, each with its own temperature and density. These pockets act like tiny lenses, bending light in slightly different directions from one moment to the next. So instead of following a perfectly straight path into your eye, the light is gently redirected again and again in rapid succession. The result is not a blur but a subtle variation. A change in brightness here, a slight shift in position there. Small enough to seem delicate, but fast enough to create the impression of flickering. What is especially striking is how concentrated this effect is. After travelling for years through the calm vacuum of space, The light is only significantly disturbed in the final fraction of a second as it passes through the atmosphere just above you. It is as if the entire journey is quiet and steady, right up until the very last moment. And that contrast is important, because it tells us that the twinkling we observe is not a feature of the universe at large, but a local effect. It is something that happens close to home, shaped by the conditions of our own planet. If you could remove the atmosphere entirely, or observe from a point far above it, the stars would appear steady and unmoving. Their light would arrive without the final distortions that give rise to twinkling. In that sense, the atmosphere is both a window and a filter. It allows us to see the stars, but it also reshapes what we see. And in doing so, it adds a subtle, ever-changing signature to the night sky. A signature that belongs not to the stars, but to Earth itself. As starlight reaches the final moments of its long journey, it arrives at something far more complex than the vast emptiness it has just crossed. It meets the atmosphere of Earth. From a distance, the atmosphere might seem like a thin, uniform shell surrounding the planet. A soft blue layer, calm and consistent. But in reality, it is anything but uniform. It is a deeply layered, constantly shifting system, shaped by temperature, pressure, motion, and energy flowing through it at every moment. To understand what happens to light here, it helps to think of the atmosphere not as a simple layer, but as a structured medium with depth and variation. Closest to the surface lies the troposphere, extending upward for roughly 10 to 15 kilometers, depending on location and weather conditions. This is where most of the air we interact with exists. It is also where clouds form, where winds move, and where temperature changes most actively occur. Above that sits the stratosphere, more stable in some ways, yet still part of the larger system. Higher still are the mesosphere and thermosphere, each with their own properties, though their influence on visible starlight is less direct than the lower layers. What matters most for our experience of twinkling is not simply that these layers exist, but that they are not uniform within themselves. Air is constantly in motion. Warm air rises, cool air sinks, winds shift across the surface, and energy from the sun drives continuous changes in temperature and pressure. These variations create gradients. A gradient in this context is simply a gradual change in a property, such as temperature or density over distance, and those gradients are everywhere. In some regions, the air is slightly warmer and less dense. In others, it is cooler and more compressed. These differences might seem small, but they are enough to influence how light travels. To explore this more deeply, we can turn to the work of Wilhelm Bjerknes, a pioneer in atmospheric science. In the early 20th century, he helped establish the foundations of modern weather prediction by treating the atmosphere as a system governed by physical laws, particularly those of fluid dynamics and thermodynamics. Bjerknes showed that the atmosphere behaves as a fluid, meaning it flows, shifts, and evolves according to forces and energy exchanges. This perspective allows scientists to model how air moves, how pressure systems develop, and how temperature differences drive motion. And crucially, it also helps us understand how light interacts with this moving medium. Because once we recognize the atmosphere as a fluid, we can begin to see it not just as air, but as something more dynamic. Something that can act, in a sense, like an optical system. Light travels at different speeds depending on the medium it moves through. In a vacuum, it travels at its maximum speed. In air, it slows slightly. The exact speed depends on the density and composition of the air. This brings us to an important concept known as the refractive index. The refractive index describes how much a medium slows down light compared to a vacuum. Even small changes in density lead to small changes in refractive index. And when the refractive index changes from one region to another, light does not continue in a perfectly straight line. It bends. This bending is called refraction. In a perfectly uniform atmosphere, where density changes smoothly and predictably, refraction would simply shift the apparent position of a star slightly. In fact, this does happen. Stars near the horizon appear slightly higher in the sky than they truly are, due to the bending of light through the atmosphere. But that effect is steady and predictable. What creates twinkling is something more complex. Because the atmosphere is not a smooth gradient, it is filled with constantly moving pockets of air, each with slightly different temperatures and densities. These pockets are not fixed in place. They form, shift, mix, and dissipate continuously. So instead of light passing through a uniform medium, it moves through a constantly changing landscape of refractive conditions. You can imagine this as a series of invisible lenses, each one slightly different, drifting and evolving in real time. As starlight passes through these regions, its path is altered again and again in small, rapid ways. Not enough to completely blur the image, but enough to introduce variation. The atmosphere, in this sense, becomes a kind of fluid optical system. Not designed or stable like a glass lens, but dynamic and ever-changing. It reshapes incoming light moment by moment, creating subtle fluctuations in how that light reaches your eyes. And because these changes happen quickly, the result is not a slow shift, but a rapid, almost shimmering effect. It is worth noting just how small these variations are. The changes in refractive index caused by temperature differences in the atmosphere are tiny, often only a fraction of a percent. But because light travels so quickly, and because it is so sensitive to changes in medium, even these small differences are enough to alter its path. Over distances of several kilometers, these tiny changes accumulate. A slight bend here, a small shift there, and by the time the light reaches you, those small variations have become noticeable as changes in brightness and position. There is also an important thermodynamic aspect to this process. Temperature differences in the atmosphere are not random. They are driven by energy flow. The sun heats the surface of the Earth unevenly, creating regions of warm and cool air. These differences drive convection, where warm air rises and cool air sinks, setting the atmosphere into motion. This motion is continuous and complex. It creates what physicists describe as a non-uniform medium, where properties vary in both space and time. And because these variations are constantly evolving, the path of light through the atmosphere is never exactly the same from one moment to the next. So even though the star itself is steady, the medium through which its light travels is not. And that distinction is key, because it means that twinkling is not a property of the light source, but a property of the medium it passes through. As starlight enters the atmosphere, it transitions from a calm, stable journey into a dynamic and fluctuating environment. The final segment of its path is shaped by processes that are rooted in fluid dynamics, thermodynamics, and optical physics, and these processes work together in a way that is both precise and unpredictable. Precise because they follow well-understood physical laws, unpredictable because the exact state of the atmosphere is constantly changing. This combination sets the stage for what comes next, because once we understand that light is being bent and redirected by a moving non-uniform medium, we can begin to explore how those changes translate into the visible effect we recognize as twinkling. And to do that, we need to look more closely at refraction itself, and at how small variations in the path of light can create the gentle flicker we see in the night sky. To understand why starlight shifts and flickers as it passes through the atmosphere, we need to look more closely at how light behaves when it moves from one medium into another. This behavior is known as refraction, and it is one of the most fundamental principles in optics. At its simplest, refraction describes the bending of light as it changes speed. When light travels through empty space, it moves at its maximum possible speed. But when it enters a material such as air, water, or glass, it slows down slightly. The exact amount of slowing depends on the properties of the material, particularly its density and composition. This change in speed is what causes light to change direction. One of the most widely used ways to describe this process is through Snell's law, which provides a precise relationship between the angle at which light enters a new medium and the angle at which it continues through that medium. In words, Snell's law tells us that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the ratio of the refractive indices of the two media. That may sound a little dense at first, but the idea behind it is quite intuitive. When light crosses a boundary between two materials with different refractive indices, part of the wave slows down before the rest. This uneven change in speed causes the direction of the wave to shift. If the light enters at an angle, the result is a bend in its path. You may have seen this effect when looking at a straight object, like a straw placed in a glass of water. The straw appears bent at the surface. That visual shift is refraction in action. But while Snell's law describes what happens at a clear boundary between two materials, such as air and water, the atmosphere presents a more subtle situation. There is no sharp boundary between layers of air. Instead, the properties of the air change gradually, forming what physicists call a gradient. This brings us to a deeper principle known as Fermat's principle of least time. Fermat's principle states that light travels along the path that takes the least time, not necessarily the shortest distance. When light moves through a medium where its speed varies from place to place, it continuously adjusts its path to maintain this principle. In a uniform medium, the fastest path is a straight line. But in a medium where the speed of light changes gradually, the fastest path becomes a curve. So instead of bending once at a boundary, the light bends continuously as it moves through regions of slightly different density. This kind of behavior is described in what is known as gradient index optics, often shortened to grin optics. In a grin medium, the refractive index changes smoothly across space rather than abruptly at a surface. This causes light to follow gently curved paths. The atmosphere is a natural example of a grin medium. Temperature differences, pressure variations, and changes in air composition all contribute to small variations in refractive index. These variations are not fixed. They shift constantly as air moves and mixes, creating a complex and ever-changing optical environment. To better understand how light responds to this, it helps to move beyond thinking of light as a simple ray, and instead consider it as a wave. This perspective was developed in part by Augustin Jean Fresnel, who contributed significantly to the wave theory of light in the early 19th century. Fresnel showed that light behaves as a wave, with properties such as interference and diffraction that cannot be fully explained by treating it as a simple particle. When we think of light as a wave, we can imagine it as a series of wavefronts. A wavefront is a surface over which the light has the same phase, meaning that all points on the surface are oscillating in sync. As a wavefront moves through space, it advances smoothly. But when it enters a medium with varying refractive properties, different parts of the wavefront can slow down by slightly different amounts. This causes the shape of the wavefront to change. Instead of remaining flat and uniform, the wavefront becomes distorted. Some parts advance more quickly, others more slowly, and the overall direction of the wave shifts accordingly. In a stable, uniform medium, these distortions would be minimal and consistent. But in the atmosphere, where conditions are constantly changing, the distortions vary from moment to moment. This is where small differences begin to matter. Even a tiny variation in temperature, perhaps just a fraction of a degree, can change the density of air enough to slightly alter its refractive index. These changes may seem insignificant, but over distances of several kilometers, they can accumulate and produce noticeable effects. To give a sense of scale, the refractive index of air at standard conditions is only slightly greater than 1. The variations caused by atmospheric changes are often on the order of 1 part in a million or less. And yet, because light is so sensitive to changes in medium, even these minute differences can bend its path by small but measurable amounts. When many such variations occur along the path of a single beam of light, the result is a constantly shifting trajectory. Now imagine not just one beam of light, but the entire wavefront arriving from a distant star. Each part of that wavefront passes through slightly different regions of the atmosphere, each with its own refractive properties. So different parts of the wavefront are bent in slightly different ways. This leads to variations in how the light is focused as it reaches your eye. Sometimes the light is concentrated slightly more, making the star appear brighter. Other times it is spread out slightly, making the star appear dimmer. At the same time, the apparent position of the star can shift by tiny amounts as the direction of the incoming light changes. These changes happen rapidly, often many times per second, because the atmosphere itself is constantly in motion. The result is the gentle flickering we recognize as twinkling. What makes this especially interesting is how such small physical changes can produce noticeable visual effects. The human eye is very sensitive to changes in brightness, particularly in low-light conditions. Even slight variations can stand out against the dark background of the night sky. So while the underlying changes in the light are subtle, their impact on perception is amplified. It's also worth noting that this effect depends on the size of the light source. Stars are so distant that they appear as point sources of light. This means that all the light we see from a star arrives along nearly the same path. Any distortion in that path affects the entire image. In contrast, larger objects in the sky, such as planets, send light along many slightly different paths. These variations tend to average out, reducing the overall effect of atmospheric distortion. But for stars, there is no such averaging. Each small change in the atmosphere directly influences how the light reaches your eye, so the combination of wave behavior, gradient refractive index, and continuous atmospheric motion creates a system where tiny variations in physical conditions lead to visible changes in brightness and position. It is a delicate process, driven by precise physical laws, yet shaped by constantly changing conditions. And it all unfolds in the final moments before the light reaches you. What began as a steady stream of photons travelling across vast distances with remarkable consistency becomes a dynamic and ever-changing signal as it passes through the atmosphere. Not because the light itself has changed, but because the medium through which it travels is in motion. And that motion, subtle as it may be, is enough to transform a steady point of light into something that appears to shimmer, flicker, and gently dance in the night sky. If the atmosphere were perfectly still, starlight would pass through it in a smooth and predictable way. The position of each star might shift slightly due to refraction, but it would remain steady, calm, and unwavering. But the atmosphere is not still. It is in constant motion, filled with flows, eddies, and swirling patterns that change from moment to moment. This motion is what physicists describe as turbulence, and it is one of the most complex and fascinating behaviors found in nature. At first glance, turbulence can seem like pure randomness. Air moves unpredictably, forming irregular patterns that are difficult to follow or predict. But beneath that apparent disorder lies a deeper structure. Turbulence is not simply chaos, it is structured chaos. To understand this, we can begin with the work of Lewis Fry Richardson, one of the early pioneers in the study of atmospheric motion. In the early 20th century, Richardson attempted to model weather by breaking the atmosphere into small regions and calculating how each one would evolve over time. While his methods were limited by the computational tools available at the time, his ideas laid important groundwork for modern fluid dynamics. Richardson also introduced a way of thinking about turbulence that remains influential. He described how large motions in the atmosphere can break down into smaller and smaller motions, forming a cascade of energy across different scales. This idea was later formalized by the Russian mathematician Andrei Kolmogorov, whose work in the 1940s provided a statistical description of turbulence. Kolmogorov's energy cascade theory explains how energy introduced into a fluid, such as air, at large scales, gradually transfers to smaller scales. For example, large air currents driven by temperature differences or wind patterns can break into smaller swirls, which then break into even smaller ones, continuing down to very fine scales, where the energy is eventually dissipated as heat. This process creates a wide range of motion, from large, slow-moving structures to tiny, rapidly changing fluctuations. And all of these motions exist simultaneously. In the atmosphere, this means that at any given moment there are countless pockets of air, each moving slightly differently, each with its own temperature, density, and velocity. These pockets are not isolated. They interact, merge, stretch, and dissolve, creating a continuously evolving pattern. This is where the connection to light becomes especially important. Because each of these pockets of air has a slightly different refractive index, the path of light passing through them is constantly being altered. As the air moves, these refractive variations shift, causing the path of the light to change in real time. So instead of travelling along a fixed, predictable route, the light is gently redirected again and again by the moving structure of the atmosphere. To describe this behavior more precisely, physicists often think in terms of statistical patterns rather than exact predictions. The exact motion of any single parcel of air may be unpredictable, but the overall properties of turbulence can still be understood and described. This is where the concept of chaos becomes relevant. In the 1960s, Edward Lorenz, a meteorologist and mathematician, discovered something remarkable while studying simplified models of atmospheric motion. He found that even very small differences in initial conditions could lead to vastly different outcomes over time. This sensitivity to initial conditions became a defining feature of what is now known as chaos theory. Lorenz famously illustrated this idea with what is often called the butterfly effect, suggesting that something as small as the flap of a butterfly's wings could, in principle, influence the development of a storm far away. While this idea is often presented in a dramatic way, its underlying meaning is quite precise. In a chaotic system, small changes grow over time, making long-term prediction extremely difficult. The atmosphere is one such system. This means that even if we could measure the exact state of the atmosphere at one moment, predicting its detailed behavior far into the future would still be challenging. For starlight passing through the atmosphere, this has a direct consequence. The exact path that the light takes is influenced by the precise arrangement of temperature and density variations in the air at that moment. As those variations change, even slightly, the path of the light changes as well. And because these changes happen continuously, the light arriving at your eye is never exactly the same from one moment to the next. This creates a dynamic pattern of brightness and position, which we perceive as twinkling. What is important to recognize is that this is not random noise in the usual sense. It is the result of a complex structured system operating across many scales. Large-scale motions in the atmosphere, such as wind patterns and thermal convection, set the overall structure. Within that structure, smaller and smaller variations emerge, each contributing to the final effect. It is a layered process, with influences ranging from kilometers down to millimeters. And because light interacts with all of these scales as it passes through the atmosphere, the resulting effect is rich and constantly changing. There is also a temporal aspect to this process. The atmosphere evolves over time, with changes occurring on timescales ranging from seconds to minutes and beyond. Some variations are slow and gradual, while others are rapid and fleeting. The flickering of stars reflects this temporal complexity. Some changes in brightness happen quickly, creating a rapid shimmer. Others occur more slowly, producing gentle variations over a longer period. Together, these effects create the characteristic appearance of twinkling. It is not a single, uniform flicker, but a combination of many overlapping variations, each driven by the underlying dynamics of the atmosphere. If we could somehow freeze the atmosphere in place, capturing all of its variations at a single moment, the twinkling would stop. The light would still be slightly distorted, but the distortions would remain fixed. It is the motion of the atmosphere, its constant evolution, that brings the effect to life. And this motion is guided by the principles of fluid dynamics, thermodynamics, and chaos theory. So when you look up at a twinkling star, you're not just seeing light from a distant object. You're also seeing the imprint of a complex system unfolding above you, a system that is structured yet unpredictable, ordered yet dynamic, and quietly shaping the light of the cosmos in its final moments before it reaches your eyes. There is something almost poetic in that. After travelling across the calm and steady expanse of space, the light encounters a region of intricate motion, where small variations are amplified into visible effects. It is as if the atmosphere adds its own signature to the light, a subtle pattern created by the interplay of energy, motion, and structure. And that pattern, ever-changing and never quite the same, is what gives the stars their gentle, shimmering appearance. As light from a distant star passes through the atmosphere, it does not arrive as a single, simple beam. It arrives as a wave, not a visible ripple like water, but a structured pattern of oscillating electric and magnetic fields, moving together through space. One of the most useful ways to understand this is to imagine the light as a series of wavefronts. Each wavefront is like a thin, invisible surface moving forward, with every point on it oscillating in sync. In empty space, far from any disturbances, these wavefronts remain smooth and uniform. They travel outward from the star in an orderly way, maintaining their structure over vast distances. But as soon as these wavefronts enter the atmosphere, they begin to change. Each part of the wavefront encounters slightly different conditions. Some regions of air are warmer, others cooler, some are denser, others less so. Because the refractive index depends on these properties, different parts of the wavefront slow down by slightly different amounts. This introduces something known as phase variation. The phase of a wave describes where it is in its cycle of oscillation. When a wavefront is perfectly uniform, all parts share the same phase. But when different parts of the wavefront experience different delays, the phase becomes uneven across the surface. In simple terms, the wavefront becomes distorted. Instead of being a smooth, flat surface, it becomes slightly warped, like a sheet that has been gently stretched and twisted. These distortions are not large, but they are constantly changing, shaped by the moving structure of the atmosphere. And it is this distortion that lies at the heart of twinkling. To understand how these distortions affect what we see, we need to consider how light enters the eye. When a wavefront reaches your eye, or a telescope, it is focused to form an image. In the case of a distant star, that image is extremely small, effectively a point of light. The clarity and stability of that point depend on how uniform the incoming wavefront is. If the wavefront is smooth, the light focuses cleanly, and the star appears steady. But if the wavefront is distorted, the focusing becomes imperfect. Some parts of the light arrive slightly out of phase with others, causing the light to interfere with itself. This is not interference in the sense of large, visible patterns, but rather subtle variations in how the light combines at the point of focus. Sometimes the waves reinforce each other, producing a slightly brighter point. At other times, they partially cancel out, making the point appear dimmer. These variations happen rapidly as the atmosphere continues to change. This process is known as scintillation. Scintillation is the technical term used in astronomy to describe the rapid fluctuations in brightness and position of a distant light source caused by atmospheric turbulence. It is a statistical phenomenon, meaning that it arises from the combined effect of many small random variations rather than a single predictable cause. Each tiny pocket of air contributes a small change to the path and phase of the light. Taken together, these changes produce a pattern of fluctuations that can be described statistically, even if the exact details are unpredictable. One of the key concepts used to quantify this effect is known as the Fried parameter, named after the physicist David L. Fried, who developed the theory in the 1960s. The Fried parameter, often referred to as R0, represents a characteristic length scale over which the wavefront can be considered relatively coherent, meaning that the phase variations are small. If you imagine looking at a wavefront arriving at a telescope, the Fried parameter defines the size of patches across that wavefront where the light is still mostly in phase. Within each patch, the light behaves more or less uniformly, but from one patch to another, the phase may differ significantly. In good atmospheric conditions, the Fried parameter might be on the order of 10 to 20 centimeters. In poorer conditions, it can be much smaller. This has important consequences. If the aperture of a telescope or the effective area of the eye is larger than the Fried parameter, then it collects light from multiple patches with different phases. These differences lead to interference effects that reduce image clarity and introduce fluctuations. For the human eye, which has a relatively small aperture, the situation is slightly different, but the underlying principle remains the same. The light arriving from a star is influenced by these phase variations, leading to changes in how it is focused and perceived. Now, because stars are effectively point sources, all of the light we receive from them is concentrated into a very small region. This makes them especially sensitive to these variations. Even a slight distortion in the wavefront can shift the apparent position of the star or change its brightness. And because the atmosphere is constantly in motion, these distortions are always changing. This leads to two key observable effects. The first is a change in brightness. As the wavefront fluctuates, the light may be focused more tightly or more loosely, causing the star to appear brighter or dimmer from moment to moment. The second is a slight change in position. The bending of light can cause the apparent location of the star to shift by tiny amounts, creating a subtle jittering motion. Together, these effects produce the familiar twinkling. It is not a steady flicker, but a complex pattern of variation, with changes occurring on timescales of fractions of a second. The exact pattern depends on the state of the atmosphere at that moment, including factors such as wind speed, temperature gradients, and altitude. What makes this particularly interesting is that the effect is both physical and perceptual. Physically, the light is being altered by the atmosphere in measurable ways. The wavefront is distorted, the phase varies, and the resulting intensity fluctuates. Perceptually, the human eye and brain interpret these fluctuations as a flicker, enhancing the effect and making it more noticeable. So what we experience as a gentle twinkle is actually the visible expression of a complex interplay between wave physics, atmospheric dynamics, and human perception. It is also worth noting that this effect becomes more pronounced when looking at stars closer to the horizon. In those cases, the light must pass through a greater thickness of the atmosphere, increasing the number of turbulent layers it encounters. This leads to larger distortions and more noticeable twinkling. When a star is directly overhead, the path through the atmosphere is shorter, and the effect is often less intense. So even the position of a star in the sky influences how strongly it appears to twinkle. In the end, what we are seeing is not instability in the star itself, but a constantly evolving pattern imposed on its light during the final moments of its journey, a pattern shaped by turbulence, carried through wavefront distortions, and revealed through this delicate balance of interference and perception. It is a subtle transformation, but one that turns steady light into something that feels alive. A quiet reminder that even the simplest points of light can carry the imprint of a dynamic and ever-changing world. If you take a moment to compare different objects in the night sky, you may notice something curious. While stars tend to shimmer and flicker, planets often appear calm and steady. They shine with a more constant light, rarely showing the same delicate twinkling. At first, this might seem surprising. After all, planets are also viewed through the same atmosphere, shaped by the same layers of moving air. The same turbulence is present, the same variations in temperature and density, the same shifting refractive patterns, and yet the effect is noticeably different. The key to understanding this difference lies in how light arrives from these objects, and more specifically, in a concept known as spatial coherence. To explore this, we can return to the idea of light as a wave. When light travels from a distant source, it arrives as a collection of wavefronts. For a source that is extremely far away and very small in apparent size, such as a star, these wavefronts are highly coherent across the area of your eye or a telescope. This means that the phase of the light is closely related across that region, allowing interference effects to become significant. This concept was developed in greater detail by physicists such as Emil Wolf, who contributed to the theory of optical coherence. Coherence in this context describes how well different parts of a light wave maintain a fixed relationship with one another. A highly coherent wavefront is uniform and consistent. A less coherent one is more varied, with different parts behaving more independently. Stars, because of their immense distance, appear as what physicists call point sources. Their actual size may be enormous, but from Earth, they occupy such a tiny angle in the sky that all of their light effectively arrives from a single direction. This means that the wavefronts from a star are coherent across the aperture of your eye. When atmospheric turbulence distorts these wavefronts, the entire image is affected in a unified way. Small changes in phase lead directly to changes in brightness and position, creating the familiar twinkling. Planets, on the other hand, are much closer. Even though they are still far away on a human scale, they are close enough that they appear as small disks rather than point sources. If you were to look at a planet like Jupiter or Venus through a telescope, you would see a tiny but clearly defined shape, not just a single point of light. This difference in apparent size has important consequences. Because a planet has a measurable angular size, the light reaching your eye comes from many slightly different directions. Each part of the planet's surface sends light along its own path, and those paths pass through different regions of the atmosphere. So instead of receiving a single coherent wavefront, you receive a collection of slightly different wavefronts, each affected in its own way by atmospheric turbulence. This is where averaging comes into play. The distortions caused by the atmosphere still occur, but they do not affect all parts of the image in the same way at the same time. Some regions of the incoming light may be slightly brighter, others slightly dimmer. Some may shift in one direction, others in another. When all of this light is combined in your eye, the variations tend to cancel out. The result is a more stable image. This process is similar, in a sense, to averaging multiple signals. If you take many slightly different measurements and combine them, the random fluctuations tend to smooth out, leaving a more consistent overall result. In the case of planets, the extended nature of the source provides this averaging naturally. It does not eliminate atmospheric effects entirely. If you observe a planet carefully, especially with magnification, you may still notice subtle distortions. The edges may appear to shimmer slightly, and fine details may blur or shift. But the overall brightness remains much more stable than that of a star. This difference highlights the importance of apparent size in optical systems. The human eye has a limited resolution, meaning it cannot distinguish extremely small details. Stars fall well below this resolution limit, appearing as single points. Planets, though still small, are just large enough to extend beyond that limit under the right conditions. This means that the eye processes them differently. For a point source, any fluctuation in the incoming light directly affects the entire image. For an extended source, fluctuations are distributed across the image, reducing their overall impact. There is also a connection here to the concept of spatial coherence. For a point source like a star, the light remains highly coherent across the aperture of the eye. allowing interference effects to produce noticeable intensity variations. For an extended source like a planet, the coherence is reduced. Light from different parts of the source is less correlated, making interference effects less pronounced. In simpler terms, the light from a planet is less in sync across its entire image, which makes it less sensitive to small distortions. This is why planets tend to shine with a steady, almost unwavering light, while stars flicker. It is not that the atmosphere treats them differently, but that their light interacts with the atmosphere in different ways and is then interpreted differently by our eyes. There is something quietly elegant in this distinction. Two objects, both affected by the same physical processes, can appear so different simply because of how their light is structured and how it arrives. It also offers a useful way to identify objects in the night sky. If you see a bright point of light that does not twinkle, or only twinkles very slightly, there is a good chance it is a planet. Venus, for example, often appears as a bright, steady light in the evening or morning sky. Jupiter, too, can shine with a calm, consistent glow. Stars, by contrast, tend to show that subtle, ever-changing flicker. So the next time you look up and notice a steady point of light among the twinkling stars, you're not just seeing a different object. You're seeing the result of a different interaction between light, atmosphere, and perception. A reminder that even small differences in distance and size can shape what we experience in profound ways, and that the calm steadiness of a planet, set against the gentle shimmer of the stars, is part of a larger story about how light travels, how it changes, and how we come to see it. When we look at the night sky, it is natural to think of stars as small. They appear as tiny points of light, delicate and distant, almost like fine grains scattered across a dark surface. But this appearance is not a reflection of their true size. In reality, many stars are enormous. Some are far larger than our Sun, with diameters millions of kilometers across. The reason they appear so small is not because they are small, but because they are so far away. This brings us to an important concept in optics known as angular size. Angular size describes how large an object appears in the sky, not in terms of its actual physical size, but in terms of the angle it subtends at the observer's eye. An object can be physically large, but if it is far enough away, it will occupy only a tiny angle in your field of view. Stars are the most extreme example of this. Even the nearest stars, apart from the Sun, are so distant that their angular size is extraordinarily small. For most stars, the angle they subtend is far below what the human eye or even most telescopes can resolve directly. This leads us to the concept of angular resolution. Angular resolution is the ability of an optical system, such as the human eye or a telescope, to distinguish between two closely spaced points of light. It defines the smallest angle at which two separate objects can be seen as distinct rather than blurred together. The limits of angular resolution are not determined solely by the quality of the optical system, but also by a fundamental property of light itself. This property is diffraction. Diffraction occurs because light behaves as a wave. When a wave passes through an opening such as the pupil of the eye or the aperture of a telescope, it spreads out slightly. This spreading limits how sharply an image can be focused. Even with a perfect optical system, there is a minimum size to which a point of light can be focused. This is known as the diffraction limit. Ernst Abbe, a physicist working in the 19th century, played a key role in establishing the relationship between wavelength, aperture size, and resolution. His work showed that the resolving power of an optical system depends on both the size of the aperture and the wavelength of the light being observed. In simple terms, larger apertures can resolve finer at a tafassil, while shorter wavelengths allow for higher resolution. But no matter how perfect the system is, diffraction imposes a fundamental limit. For the human eye, this limit is relatively modest. The pupil is only a few millimeters in diameter, and the wavelengths of visible light are on the order of hundreds of nanometers. This means that the eye cannot resolve objects below a certain angular size. Stars fall well below this threshold, so instead of appearing as tiny disks, stars appear as point sources, not because they have no size, but because their size is too small to be resolved. This has important consequences. When an object is resolved, meaning its structure can be seen, different parts of the object send light along slightly different paths. These paths can be affected differently by the atmosphere, allowing some of the distortions to average out. But when an object is unresolved, like a star, all of its light effectively arrives along the same path. There is no spatial structure to distribute or absorb the effects of atmospheric variation. This means that any distortion in the path of the light directly affects the entire image. A small change in direction shifts the apparent position of the star. A small change in phase alters its brightness. There is no averaging, no smoothing, no buffering. Everything happens all at once. This is why stars are so sensitive to atmospheric effects. Their immense distance compresses all of their spatial information into a single point. By the time their light reaches Earth, it carries almost no information about the physical size or structure of the star itself, at least in terms of direct imaging. Instead, all that remains is a concentrated signal, and that signal is easily influenced. It is also worth considering just how extreme this compression is. A star that is millions of kilometers across may appear as a point smaller than 1,000th of an arcsecond in the sky. An arcsecond is already a very small unit of angular measurement, equal to 1/3600th of a degree. So we are dealing with angles that are far beyond the resolving power of the human eye. In effect, the star becomes a mathematical point, a source of light without visible size. This makes it uniquely vulnerable to distortion, because when the wavefront of light from a point source is distorted, the entire image responds immediately. There is no redundancy, no distribution of light across a surface. Every fluctuation matters. This is quite different from what happens with closer or larger objects. For something like the Moon, which has a large angular size, different parts of its surface send light along different paths. Atmospheric distortions may blur or distort the image, but they do not cause the entire object to flicker in brightness. The same is true to a lesser extent for planets. But for stars, the situation is more delicate. Their light arrives as a tightly concentrated signal, shaped by diffraction and limited by resolution. This signal is then passed through a medium that is constantly changing. The result is a system that is highly sensitive to even the smallest variations. And that sensitivity is what allows us to see twinkling so clearly. It is not that the atmosphere is unusually strong in its effects, but that the nature of the source makes those effects more visible. In a way, the distance of the stars simplifies them. It removes their visible structure, reduces them to points, and in doing so makes their light more vulnerable to the influence of the atmosphere. So when you see a star flicker, you are witnessing the interaction between two limits. The limit imposed by diffraction, which prevents us from resolving the star's true size, and the limit imposed by the atmosphere, which introduces variations in the path of its light. Together, these limits transform a steady, distant source into something that appears dynamic and alive. A reminder that what we see is not only determined by what is out there, but also by the limits of how we are able to observe it. As starlight passes through the atmosphere, it does not encounter a single uniform layer. Instead, it moves through a series of regions, each with its own structure, motion, and influence on the path of light. These layers are not neatly separated in a way that light can clearly distinguish. Rather, they blend into one another, forming a continuous system that varies both vertically and horizontally. And within this system, different scales of motion and variation coexist, each contributing to the final effect we observe. One of the most important regions for understanding twinkling is the boundary layer. The boundary layer is the lowest part of the atmosphere, extending from the surface of the Earth up to roughly 1 or 2 kilometers, though its exact height changes depending on weather conditions and time of day. This is where the atmosphere interacts most directly with the surface. During the day, sunlight heats the ground unevenly. Some surfaces absorb more energy than others. Dark soil warms more quickly than reflective surfaces, and urban areas can retain heat differently than open land or water. This uneven heating creates temperature differences in the air just above the surface. Warm air rises, cool air sinks, and this motion generates turbulence. At night, the situation changes. The ground cools, often more rapidly than the air above it. This can create temperature inversions where cooler air sits beneath warmer air. Even in these conditions, the boundary layer remains active, with subtle flows and mixing continuing to reshape the structure of the air. This region is often the most turbulent part of the atmosphere, especially near the surface where obstacles like buildings, trees, and terrain disrupt the flow of air. From the perspective of starlight, the boundary layer acts as a highly dynamic optical environment. It contains countless small pockets of air with slightly different temperatures and densities, each capable of bending light in small but meaningful ways. As light passes through this region, it is subjected to rapid, fine-scale variations. But the boundary layer is only part of the story. Above it lies the free atmosphere, which includes higher layers such as the upper troposphere and the lower stratosphere. These regions are generally less influenced by direct contact with the surface, but they are far from static. Large-scale air movements occur here, driven by global circulation patterns. One of the most significant features in these higher layers is the jet stream. Jet streams are narrow bands of strong winds that flow through the upper troposphere, typically at altitudes of around 10 kilometers. These winds can reach speeds of over 100 kilometers per hour, and they play a key role in shaping weather patterns across the planet. From an optical perspective, jet streams introduce another layer of complexity. The fast-moving air within a jet stream creates shear, meaning that adjacent layers of air move at different speeds or in different directions. This shear generates turbulence, though often on larger scales than those found in the boundary layer. These higher altitude disturbances can still affect the path of starlight, especially because they occur earlier in the light's passage through the atmosphere. Even small deviations introduced at high altitude can influence how the light interacts with lower layers later on. This layered interaction creates a cumulative effect. Each region of the atmosphere contributes its own variations, and these variations combine to produce the final distortion of the wavefront. This is why the atmosphere is often described as a multi-scale system. Different processes operate at different sizes and speeds. Large-scale motions, such as global wind patterns, set the overall structure. Medium-scale processes, like jet stream turbulence, add additional variation. And small-scale motions in the boundary layer introduce rapid, fine, detailed changes. All of these scales overlap and interact. The result is a complex, continuously evolving environment through which light must pass. Another important factor is the vertical variation in refractive index. As altitude increases, the density of air decreases. This means that the refractive index of the atmosphere changes with height. In general, light bends slightly as it passes through this gradient, even in the absence of turbulence. This is why stars near the horizon appear higher than their true position. The light from those stars travels through a thicker layer of atmosphere, experiencing more refraction overall. But when turbulence is added to this vertical gradient, the situation becomes more complex. Instead of a smooth change in refractive index, there are fluctuations superimposed on the gradient. These fluctuations vary in both space and time, creating a constantly shifting pattern of refraction. It is helpful to think of the atmosphere as a layered lens, but one that is constantly changing shape. Unlike a glass lens, which has a fixed form and predictable optical properties, the atmosphere is fluid and dynamic. Its shape is defined by the distribution of temperature and density at any given moment, and that distribution is always evolving. Sverre Pettersen, a meteorologist known for his work in atmospheric dynamics, contributed to our understanding of how these large-scale and small-scale processes interact. His research helped clarify how different layers of the atmosphere influence one another, and how energy is transferred across scales. This perspective is essential when considering optical effects, because the light does not simply pass through one layer at a time in isolation. It moves through a system where each layer has already been influenced by the ones above and below it. The distortions introduced at one level can be modified, amplified, or partially corrected by conditions in another. This interplay creates a rich and complex pattern of variation. Sometimes the effects from different layers combine in a way that enhances distortion, leading to stronger twinkling. At other times, they may partially cancel out, resulting in a calmer appearance. The exact outcome depends on the state of the atmosphere at that moment. This is why twinkling can vary from night to night, and even from minute to minute. On some nights, the stars appear relatively steady, with only a gentle shimmer. On others, they flicker more dramatically, their brightness changing rapidly and noticeably. These differences reflect changes in the structure and motion of the atmosphere. Calmer conditions with less turbulence and more uniform temperature gradients produce less distortion. More active conditions with stronger winds and greater temperature variation increase the effect. What is remarkable is that all of this complexity unfolds in a layer of air that is, on a planetary scale, quite thin. The atmosphere extends upward for tens of kilometers, but compared to the size of the Earth, this is a very small fraction. And yet, within this thin layer, an intricate system of motion and variation exists, capable of reshaping the light of distant stars. So when you look up and see a star twinkle, You are seeing the combined effect of processes occurring across multiple layers of the atmosphere. From the smallest eddies near the ground to the fast-moving currents high above, each layer leaves its mark on the light, and together they create a dynamic optical environment, one that transforms steady starlight into the gentle, ever-changing flicker that we observe. A subtle reminder that even the air above us, invisible and often unnoticed, is filled with motion, structure, and influence. The way a star twinkles on any given night is not fixed. It changes, sometimes subtly, sometimes quite noticeably, depending on the state of the atmosphere above you. If you spend enough time observing the night sky, you may begin to notice patterns. Some evenings feel calm, with stars that shimmer only gently, almost steadily. On other nights, the same stars may flicker more intensely, their brightness shifting rapidly, their positions seeming to tremble. These differences are not random. They are shaped by the same factors that influence our everyday weather. At the heart of this connection are temperature gradients and wind. A temperature gradient simply refers to a difference in temperature over distance. In the atmosphere, these gradients are everywhere. Warm air near the surface, cooler air above. Pockets of varying temperature drifting and mixing. These differences in temperature lead directly to differences in air density. And as we have seen, density affects the refractive index of air. So whenever there are temperature gradients, there are also variations in how light travels. Wind adds another layer to this process. Air is rarely still. Even on nights that feel calm at ground level, there may be significant motion higher up. Wind transports pockets of air with different temperatures and densities, moving them across the path of incoming starlight. This motion causes the refractive structure of the atmosphere to change continuously. The faster the air moves, and the more irregular the temperature distribution, the more rapidly the light path shifts. This leads to stronger and more frequent fluctuations in brightness and position. In astronomy, these conditions are described using a term known as seeing. Seeing refers to the quality of the atmosphere for observing astronomical objects. It is not about whether the sky is clear or cloudy, but about how stable the air is. Good seeing conditions occur when the atmosphere is relatively calm, with minimal turbulence and smooth temperature gradients. Under these conditions, starlight is only slightly distorted, and stars appear more steady. Poor seeing conditions occur when the atmosphere is more active, with strong turbulence and rapidly changing temperature differences. In these cases, starlight is more heavily distorted, and stars twinkle more noticeably. Professional observatories pay close attention to seeing. In fact, some of the world's most advanced telescopes are located in places chosen specifically for their stable atmospheric conditions. High-altitude sites, such as those in the Atacama Desert or on volcanic peaks in Hawaii, are often preferred because they lie above much of the turbulent boundary layer and experience more consistent airflow. These locations offer clearer, steadier views of the sky. This pursuit of stability is not new. In the 19th century, astronomers like William Huggins were already striving for greater precision in their observations. Huggins was one of the first to use spectroscopy to analyze the light from stars, revealing information about their composition and motion. For such work, clarity was essential. Even small distortions in the light could affect the accuracy of measurements. This led to an early appreciation of how atmospheric conditions influence observation, long before the detailed physics of turbulence was fully understood. Today, the concept of seeing is often quantified using measures like the Fried parameter, which describes the coherence of the incoming wavefront. But even without technical instruments, the effects are visible to the naked eye. You can see them simply by looking up. On a night with stable air, stars may appear almost steady, with only a faint shimmer. On a more turbulent night, they may flicker more dramatically, their light dancing in a way that is easy to notice. These changes can occur not only from night to night, but within a single evening. As the temperature of the ground changes, as winds shift, as air masses move, the structure of the atmosphere evolves. A calm period may give way to more active conditions, or vice versa. This reflects the underlying nature of the atmosphere as a chaotic system. As described in chaos theory, small changes in initial conditions can lead to large differences in outcomes over time. In the context of weather, this means that even minor variations in temperature or pressure can influence the development of atmospheric patterns. And because these patterns affect turbulence, they also influence how starlight behaves. This unpredictability is part of what makes the sky feel alive. There is no single, fixed pattern to the twinkling. It is always changing, shaped by processes that are both governed by physical laws and sensitive to small variations. At the same time, there are general trends. Clear, cold nights with little wind often provide better seeing. The atmosphere tends to be more stable, with fewer strong temperature gradients. Warm, windy conditions, on the other hand, are more likely to produce stronger turbulence and more noticeable twinkling. Even the time of day can play a role. After sunset, the ground begins to cool, and the atmosphere adjusts to the changing temperature. This transition period can sometimes lead to increased turbulence, as different layers of air mix and settle. Later in the night, conditions may stabilize, leading to calmer air and steadier stars. So the appearance of the night sky is not just a function of what is out there in space, but also of what is happening here on Earth. The same forces that shape clouds, winds, and weather patterns are also shaping the light of the stars as it reaches you. There is something quietly reassuring in that connection. The sky above is not separate from the world around you. It is linked to it, influenced by the same processes that move the air you breathe and shape the environment you experience each day. So when you notice that the stars are twinkling more brightly on one night than another, you're not just seeing a distant phenomenon. You're seeing the atmosphere in motion, a dynamic, ever-changing system, gently revealing itself through the light of the stars. If you watch a bright star carefully, especially one that sits low in the sky, you may notice something beyond the gentle flicker of its light. Along with changes in brightness, there are often brief flashes of colour. For a moment, the star may appear slightly red, then perhaps a hint of blue, then white again, or something in between. These colour shifts are subtle and fleeting, but once you notice them, they become difficult to ignore. This effect is known as chromatic scintillation. To understand why it happens, we need to consider an important property of light. Light is not a single uniform entity. It is made up of a range of wavelengths, each corresponding to a different colour. Red light has a longer wavelength, while blue light has a shorter one, with other colours falling in between. When light passes through a medium, its speed depends slightly on its wavelength. This means that different colours of light are refracted by slightly different amounts. This phenomenon is called dispersion. A familiar example of dispersion can be seen in a prism. When white light enters a prism, it spreads out into a spectrum of colours, because each wavelength is bent by a slightly different angle. The same principle applies in a much more subtle way as starlight passes through the atmosphere. The atmosphere, like the prism, acts as a dispersive medium. Although the effect is much weaker than in glass, it is still present. As light from a star travels through layers of air with varying refractive indices, different wavelengths follow slightly different paths. This means that red light and blue light from the same star do not arrive at exactly the same place at exactly the same time. Now, under perfectly stable conditions, this separation would be small and steady. The star might appear slightly tinted near the horizon, often taking on a warmer reddish hue due to the longer path through the atmosphere. This is related to another well-known effect called Rayleigh scattering, described by Lord Rayleigh, whose full name was John William Strutt. Rayleigh showed that shorter wavelengths of light, such as blue, are scattered more strongly by small particles in the atmosphere than longer wavelengths, such as red. This is why the sky appears blue during the day, and why the sun often appears red at sunrise and sunset. But chromatic scintillation involves more than just scattering. It arises from the combination of dispersion and turbulence. As we have seen, the atmosphere is not uniform. It contains constantly moving pockets of air with different temperatures and densities. These variations affect how light is refracted, and because refraction depends on wavelength, they affect different colours in slightly different ways. So as the atmosphere shifts, the paths of red, blue, and other wavelengths shift independently. At one moment, the conditions may cause more red light to be directed toward your eye, making the star appear slightly reddish. A fraction of a second later, a different configuration of the atmosphere may favour blue light, giving the star a bluish tint. These changes happen rapidly, often many times per second. The result is a subtle, flickering display of colour. It is important to note that the star itself is not changing colour in this way. Its intrinsic colour remains constant, determined by its temperature and composition. What we are seeing is a variation in how different parts of its spectrum are being redirected by the atmosphere. This makes chromatic scintillation a kind of filtering effect. The atmosphere is not simply dimming or brightening the light as a whole, It is selectively altering the contribution of different wavelengths moment by moment. The effect tends to be more noticeable for stars near the horizon. When a star is low in the sky, its light must pass through a thicker layer of atmosphere. This increases both the overall amount of refraction and the degree of dispersion. It also means that the light encounters more turbulent regions, amplifying the variations. As a result, stars near the horizon often show more pronounced colour changes, sometimes appearing to flash red, blue and white in quick succession. Higher in the sky, where the path through the atmosphere is shorter, the effect is usually less intense. There is also an interesting connection between chromatic scintillation and other atmospheric optical phenomena. For example, the same principles of dispersion and scattering are responsible for the formation of rainbows. In that case, sunlight is refracted and reflected within water droplets, separating into its component colours. Similarly, halos around the sun or moon are caused by light interacting with the ice crystals in the upper atmosphere, producing patterns of colour through refraction and diffraction. In each of these cases, the atmosphere acts as an optical system, shaping light in ways that reveal its underlying structure. Twinkling stars, with their subtle colour shifts, are another expression of this same principle. They show us that even in the absence of dramatic effects like rainbows or halos, the atmosphere is constantly interacting with light, gently reshaping it in ways that are visible if we look closely. There is something quietly intricate about this. A distant star emits a steady spectrum of light, shaped by processes deep within its core. That light travels across space unchanged, carrying information about the star's temperature, composition and energy output. And then, in the final moments of its journey, it is filtered through a dynamic and ever-changing medium. The atmosphere takes that steady signal and introduces variation, not just in brightness, but in colour. It does so in a way that is subtle, almost delicate, yet grounded in precise physical principles. So when you see a star briefly flash with a hint of red or blue, you're witnessing the combined effects of dispersion, turbulence, and the wavelength-dependent nature of light. A small but beautiful reminder that even the colours we see in the night sky are shaped not only by the stars themselves, but by the invisible motions of the air above us. And that within the quiet flicker of a single point of light, there is a rich interplay of physics unfolding in real time. When you look up at a twinkling star, it can feel as though you are directly witnessing something happening in the sky. A light that brightens, dims, and shifts all in real time. But what you're actually experiencing is not just a physical process in the atmosphere. It is also a process within your own visual system. The human eye and brain do not simply record light as it arrives. They interpret it, process it, and reconstruct it into a coherent experience. This means that twinkling is not only about what the light is doing, but also about how your visual system responds to those changes. To understand this, we can begin with the idea of temporal resolution. Temporal resolution refers to the ability of the visual system to detect changes over time. It defines how quickly the eye can respond to fluctuations in light, and how rapidly those changes can occur before they blur together into a steady signal. The human visual system is quite sensitive in this regard. Under typical conditions, the eye can detect changes in brightness that occur on the order of tens of milliseconds. This means that if the intensity of light varies several times per second, those variations can be perceived as flicker. The fluctuations caused by atmospheric turbulence often fall within this range. As the wavefront of starlight is distorted, the brightness of the star changes rapidly, sometimes many times per second. These changes are fast enough to be detected, but not so fast that they blend into a continuous signal. So instead of seeing a steady light, you perceive a flicker. This flicker is further shaped by the structure of the eye itself. The retina, located at the back of the eye, contains two main types of photoreceptor cells, known as rods and cones. Rods are highly sensitive to light and are responsible for vision in low-light conditions, such as at night. Cones are less sensitive, but are responsible for colour vision and fine detail. When you look at stars in the night sky, you are primarily using your rods. Rods are excellent at detecting faint light, but they have relatively low spatial resolution and limited ability to distinguish colour. They are also particularly sensitive to changes in brightness over time. This makes them well suited to detecting the subtle fluctuations caused by atmospheric turbulence. As the brightness of a star varies, the rods in your retina respond quickly, sending signals to the brain that reflect those changes. But the process does not end there. The signals from the retina are transmitted through the optic nerve to the visual cortex, where they are processed and interpreted. This processing involves combining information from many photoreceptors, filtering noise, and constructing a stable representation of the visual scene. Hermann von Helmholtz, a 19th century scientist who made significant contributions to the study of vision, proposed that perception is not a passive recording of sensory input, but an active process of interpretation. According to Helmholtz, the brain uses unconscious inference to make sense of the information it receives. It draws on prior experience, expectations, and patterns to construct what we perceive as reality. In the case of twinkling stars, this means that the brain is not simply reporting raw fluctuations in light. It is organizing those fluctuations into a meaningful pattern. Small, rapid changes in brightness and position are interpreted as a flicker or shimmer. The brain enhances the sense of variability, making the effect more noticeable and coherent. This is why twinkling feels like a distinct visual phenomenon, rather than a random collection of small changes. There is also an important interaction between spatial and temporal processing. Because stars appear as point sources, their light is concentrated into a very small area on the retina. This means that even slight changes in intensity are not spread out over a larger image, but are focused on a small group of photoreceptors. This concentration amplifies the effect of fluctuations. If the same variations in light were distributed across a larger image, as with a planet or the moon, they would be less noticeable. But for a star, the entire signal is confined to a tiny region, making it more sensitive to change. The brain then interprets these changes over time, creating the impression of twinkling. It is also worth noting that perception is influenced by context. When you look at a star in isolation, against a dark background, even small variations can stand out clearly. There are no nearby visual references to stabilize the image, so the flicker becomes more prominent. In contrast, when you look at larger objects or scenes with more visual detail, the brain has additional information to work with, which can reduce the perceived impact of small fluctuations. So the experience of twinkling is shaped not only by the physical properties of light and atmosphere, but also by the way the visual system processes and interprets that information. It is a combination of physics and biology. The atmosphere introduces variations in the light, and the eye and brain transform those variations into a perceptual experience. This perspective also highlights an important idea. What we see is not always a direct reflection of what is happening externally. It is a constructed experience, shaped by both the incoming signal and the internal processes of perception. In the case of twinkling stars, this construction is particularly elegant. A steady source of light is transformed by the atmosphere into a fluctuating signal. That signal is then interpreted by the visual system as a gentle flicker, a shimmering point in the sky. And all of this happens seamlessly, without conscious effort. So when you look up and notice the stars twinkling, you are not just observing the atmosphere. You're also observing the remarkable ability of your own visual system to detect, interpret, and bring meaning to subtle changes in the world around you. A quiet collaboration between light, air, and perception unfolding in real time. For most of human history, the twinkling of stars was simply accepted as part of the night sky, a quiet, familiar detail that added beauty, but also placed a limit on what could be seen. Even as telescopes became more advanced, astronomers faced a persistent challenge. No matter how carefully a telescope was built, no matter how large its mirror or how precise its optics, the atmosphere remained in the way. Light arriving from distant stars was already distorted before it ever reached the instrument. This meant that the clarity of astronomical images was often determined not by the telescope itself, but by the stability of the air above it. It was as though the final lens in every telescope was not made of glass but of moving air. In the mid-20th century, a scientist named Horace W. Babcock proposed a remarkable idea. Instead of trying to avoid atmospheric distortion entirely, what if it could be corrected in real time? Babcock suggested that if the distortions introduced by the atmosphere could be measured, then an optical system could be adjusted to cancel them out. The incoming light could be reshaped, restoring the wavefront to something closer to its original undistorted form. At the time, this idea was far ahead of what technology could achieve. Measuring and correcting such rapid, small-scale distortions required tools that did not yet exist. But as technology advanced, the concept became practical. This approach is now known as adaptive optics, At its core, adaptive optics is a system designed to measure distortions in incoming light and correct them almost instantly. It does this using a combination of sensors, mirrors, and control systems, all working together at very high speeds. The first step is to detect how the incoming wavefront has been distorted. This is done using a device called a wavefront sensor. A wavefront sensor analyzes the shape of the incoming light wave, identifying deviations from a smooth ideal form. One common type is the Shack-Hartmann sensor, which divides the incoming light into many small segments and measures how each segment is tilted or shifted. By combining these measurements, the system can reconstruct the overall distortion of the wavefront. Once the distortion is known, the next step is to correct it. This is where deformable mirrors come into play. A deformable mirror is a specially designed mirror whose surface can be adjusted in real time. It is typically equipped with many small actuators, tiny devices that can push or pull on different parts of the mirror, changing its shape by very small amounts. These adjustments are incredibly precise, often on the scale of nanometers. By altering the shape of the mirror, the system can introduce changes to the light that counteract the distortions caused by the atmosphere. In effect, the mirror reshapes the incoming wavefront, flattening it and restoring its coherence. What makes this process especially impressive is its speed. The atmosphere changes rapidly, with distortions evolving many times per second. To keep up, adaptive optics systems must measure and correct these changes in real time, often updating hundreds or even thousands of times each second. It is a continuous process of sensing and adjustment. Measure the distortion, adjust the mirror, measure again, adjust again, over and over in a seamless loop. There is, however, an important challenge. To measure the distortion of the incoming light, the system needs a reference point, a source of light that is known to be stable and well understood. For some observations, this can be a natural guide star, a bright star located near the object being studied. The system uses the light from this star to determine how the atmosphere is affecting the wavefront, but in many cases there is no suitable natural star available in the right position. To solve this, astronomers developed an ingenious solution. They create their own stars. These are known as laser guide stars. A powerful laser is projected into the upper atmosphere, typically targeting a layer rich in sodium atoms at an altitude of around 90 kilometers. When the laser light interacts with these atoms, it causes them to glow, producing a small artificial point of light in the sky. This artificial star serves as a reference for the adaptive optics system. By analyzing how the light from the laser guide star is distorted, the system can determine the current state of the atmosphere and apply the necessary corrections. It is a remarkable technique. A beam of light is sent upward into the sky, creating a point of reference, which is then used to correct the light coming down from distant stars. With adaptive optics in place, the improvement in image quality can be dramatic. Stars that once appeared blurred and unstable can become sharp and well-defined. Fine details in distant galaxies can be resolved with much greater clarity. The effects of atmospheric turbulence are not entirely eliminated, but they are significantly reduced. In some cases, ground-based telescopes equipped with adaptive optics can achieve resolutions comparable to those of space-based telescopes. This represents a major step forward in observational astronomy. It allows scientists to study distant objects with greater precision, to detect faint structures, and to explore the universe in ways that were once limited by the atmosphere. And yet, there is something interesting about this process. The same atmosphere that creates the twinkling we see with the naked eye is also the source of the distortions that astronomers work so carefully to correct. From one perspective, it is an obstacle. From another, it is a phenomenon to be understood and, when possible, compensated for. Adaptive optics does not remove the atmosphere. It works with it, measuring its effects and adjusting for them. In doing so, it reveals something deeper. The distortions we see as twinkling are not random imperfections. They are structured, measurable, and, with the right tools, correctable. They follow the same physical principles that govern light, motion, and energy. So when you look up at a twinkling star, you're seeing the uncorrected version of that light, shaped by the atmosphere in real time. And somewhere, in observatories around the world, systems are working to remove that distortion, to recover the steady light beneath. Both perspectives are valuable. One reveals the beauty of the atmosphere in motion. The other reveals the underlying clarity of the stars themselves. And together, they show how science allows us not only to understand the world as we experience it, but also to see beyond its immediate effects. If you could lift yourself gently above the atmosphere, rising higher and higher until the air below faded into a thin blue line, something subtle but profound would change. The stars would stop twinkling. They would no longer shimmer or flicker. Instead, they would appear steady, fixed, almost perfectly constant in their brightness. The gentle motion that gives the night sky its familiar texture would disappear, replaced by a quiet stillness. This change reveals something important. The twinkling we see from the ground is not a property of the stars themselves. It is something introduced by the atmosphere. Remove the atmosphere and the effect vanishes. In space, light travels through a near vacuum, an environment with almost no particles, no temperature gradients, and no turbulent motion to disturb its path. Without these variations, the wavefront of incoming light remains smooth and undistorted. This allows telescopes in space to operate under very different conditions. Instead of being limited by atmospheric turbulence, their performance is constrained only by the fundamental properties of light itself. Chief among these is diffraction. Diffraction, as we explored earlier, sets a natural limit on how sharply light can be focused. Even in perfect conditions, a point source of light cannot be imaged as a single point. Instead, it forms a small pattern determined by the wavelength of the light and the size of the telescope's aperture. This is known as diffraction-limited imaging. In a diffraction-limited system, the quality of the image is as sharp as physically possible for that instrument. There are no additional distortions from the environment. The only limitations are those imposed by the wave nature of light. Achieving this level of performance from the ground is extremely difficult, because the atmosphere constantly disrupts the incoming wavefront. Even with adaptive optics, corrections are never perfect, and some residual distortion remains. In space, however, diffraction-limited imaging becomes the standard. This is one of the key reasons why space-based telescopes have transformed our understanding of the universe. The development of these telescopes was shaped by the work of many scientists and engineers, including Nancy Grace Roman, often referred to as the mother of the Hubble Space Telescope. Her efforts in the mid-20th century helped establish the vision for placing large optical instruments above the atmosphere, where they could observe the universe without the interference of air. The Hubble Space Telescope, launched in the late 20th century, became one of the most well-known examples of this approach. From its position in low Earth orbit, it observes the cosmos with a clarity that would be impossible from the ground without extensive correction. Stars appear steady and sharply defined. Galaxies reveal intricate structures. Distant objects can be studied in detail, their light preserved in a form much closer to its original state. This clarity comes from the absence of turbulence. Without moving layers of air to bend and distort the light, the wavefront arrives intact. The image formed by the telescope reflects the true structure of the incoming light, limited only by diffraction and the design of the instrument. There is also another advantage to observing from space. The atmosphere not only distorts light, but also absorbs and scatters certain wavelengths. Some forms of electromagnetic radiation, such as ultraviolet and parts of the infrared spectrum, are partially or completely blocked by the atmosphere. By placing telescopes above the atmosphere, scientists can observe these wavelengths directly, opening up new windows into the universe. This has allowed for discoveries that would not have been possible otherwise. But even when focusing only on visible light, the difference is striking. A star observed from space does not flicker. Its brightness remains steady, its position fixed. The subtle variations we see from the ground are gone. This provides a kind of reference point. It shows us what starlight looks like when it is not shaped by the atmosphere. It reveals the underlying stability that is present all along, hidden beneath the distortions introduced during the final moments of the light's journey. At the same time, it highlights the role of the atmosphere in shaping our everyday experience of the sky. From the ground, we see a version of the stars that has been filtered, altered, and gently transformed. The twinkling we observe is a product of this interaction, a signature of the air above us. In space, that signature is absent. The stars appear as they are, steady and consistent. There is something interesting in that contrast. On one hand, the view from space offers greater clarity and precision. It allows us to study the universe in detail, to measure, analyze, and understand. On the other hand, the view from the ground carries a certain character. The twinkling adds motion, texture, and a sense of presence to the night sky. It reminds us that we are observing from within a dynamic environment, one that is constantly interacting with the light we receive. So while space-based observations reveal the true steadiness of the stars, the twinkling we see from Earth is not simply a flaw to be removed. It is a reflection of our place within the atmosphere, a quiet indication that the light reaching us has passed through a living, moving system before arriving at our eyes. And in that sense, the absence of twinkling in space does not make the stars more real. It simply shows us a different version of the same light, one without the influence of air, without the gentle distortions that turn steady points into shimmering ones. A reminder that what we see depends not only on what is out there, but also on where we are when we choose to look. When we look at a twinkling star, it is easy to think of the flicker as something purely aesthetic, a gentle, almost poetic detail in the night sky. But from a scientific perspective, that flicker is something else entirely. It is information. Every small variation in brightness, every slight shift in position, carries with it a record of the conditions the light has passed through. The atmosphere, in bending and reshaping the light, leaves behind a pattern that can be measured, analysed and understood. This turns twinkling into a useful signal. In physics and engineering, signals are often studied not just for what they represent at the source, but for how they change along the way. These changes can reveal properties of the medium through which the signal has travelled. In the case of starlight, the medium is the atmosphere, and the variations we see, known as scintillation, provide a way to study its structure. Scintillation, as we have described, refers to the rapid fluctuations in the intensity and position of a light source caused by turbulence. While this effect can make astronomical observations more difficult, it also offers an opportunity. By carefully measuring these fluctuations, scientists can infer details about the atmosphere itself. One of the key theoretical frameworks for understanding this process was developed by Vladimir Tatarsky, a physicist who studied how waves propagate through turbulent media. His work, particularly in the mid-20th century, provided a mathematical description of how fluctuations in refractive index affect the phase and amplitude of waves. Tatarsky's theory connects the statistical properties of turbulence with the observable effects on light. In simple terms, it allows scientists to relate what they measure, such as changes in brightness or phase, to the underlying structure of the atmosphere, including the distribution of temperature and density variations. This is a powerful idea. It means that by observing how light is distorted, we can learn about the invisible patterns in the air. In practice, this is done using instruments that measure scintillation in a controlled and precise way. For example, by observing the fluctuations in the light from a star over time, it is possible to estimate the strength of turbulence at different altitudes. This can be used to build a profile of the atmosphere, showing how conditions vary with height. Such measurements are important for astronomy, where understanding atmospheric conditions helps improve observations. But the applications go beyond astronomy. The same principles apply to any system where waves travel through a turbulent medium. This includes radio waves, microwave signals, and laser beams. In satellite communication, signals must pass through the atmosphere to reach receivers on the ground. Variations in the atmosphere can cause these signals to fluctuate, affecting their strength and quality. By studying scintillation effects, engineers can design systems that are more robust, capable of compensating for these variations and maintaining reliable communication. Laser systems are also affected. When a laser beam is sent through the atmosphere, whether for communication, measurement, or imaging, it can experience distortion similar to that of starlight. The beam may spread, shift, or fluctuate in intensity as it passes through turbulent air. Understanding these effects is essential for applications ranging from optical communication to remote sensing. In some cases, the goal is to minimize the impact of turbulence. In others, it is to use the information carried by the fluctuations. For example, LiDAR systems, which use laser light to measure distances and atmospheric properties, can analyze how the returning signal has been affected by the air. This provides insight into the structure and composition of the atmosphere. So what might appear as a simple flicker in the sky becomes, in a different context, a source of data, a way of probing the invisible. There is also a deeper conceptual shift here. Twinkling, which might initially seem like a limitation, something that interferes with clear observation, can be reinterpreted as a diagnostic tool. Instead of trying to eliminate it entirely, scientists can study it, extract information from it, and use it to understand the system that produces it. This approach reflects a broader principle in science. Phenomena that appear as noise or distortion can often be transformed into signals when viewed from the right perspective. The key is to understand the underlying processes well enough to interpret the patterns. In the case of atmospheric scintillation, this means combining knowledge of fluid dynamics, optics, and statistical physics. It involves measuring fluctuations, analyzing their distribution, and connecting them to models of turbulence and wave propagation. The result is a detailed picture of how the atmosphere behaves, and all of this begins with the same flicker that you can see with your own eyes. A star that brightens and dims, shifts and shimmers, not because it is changing, but because the air above you is in motion. So the next time you notice a star twinkling, it may be interesting to consider that what you are seeing is not just a visual effect. It is a trace of the atmosphere's structure, a signal carrying information about temperature, motion, and variation. A quiet reminder that even the most delicate features of the night sky can hold layers of meaning waiting to be understood, and that within the gentle flicker of a distant star there is a story not only about the cosmos, but also about the air that surrounds us here on Earth.